Hello learners, this class is for B.Sc first year second sem. Okay, B.Sc first year second sem. So the unit is thermodynamics. Okay, the unit is thermodynamics. So what is thermodynamics? Thermodynamics is a branch of physics that deals with energy, heat, work and temperature, and it also explains how thermal energy is transformed into other forms of energy. We know thermal energy can be converted into several other forms of energy. Like thermal energy can be converted to mechanical energy. How? Example, in a steam engine, heat energy converts water into steam, which can move the turbine. So we can say thermal energy is converted to mechanical energy here. That is in power plants, etc. Now thermal energy can also be converted to electrical energy, transformed to electrical energy, like in coal or nuclear generating which generates electricity. Okay, in thermal power stations which uses coal and nuclear, the heat or the thermal produces steam that can rotate turbines where electricity is generated. Okay, and next, thermal energy can be converted to light energy also. Okay, we can see a hot filament in an electric bulb glows and produces light. Okay, that is light energy. Next, thermal energy can be converted to chemical energy also. Okay, in industries and okay, okay, chemical energy. Okay, next. So in this way, we can the thermal energy is transformed into other forms of energy. So it's related to heat, energy, work, and temperature. So we are dealing with this branch of physics, which is called as thermodynamics. Okay, moving ahead, system and surroundings. What is a system? So see, the thing for which we are talking, or I can say the system refers to the thing which we focus on. Wherever we are concentrating and we are talking about something, that is called as system. So see, you can understand here, the system could be a sample of gas. If you are talking about a sample of gas, then that is a system. Okay. Next, if you are talking about a steam engine, that becomes a system. Okay, if we are talking about a runner, a marathon runner, that becomes a system. If you are talking about an earth, that becomes a system. If we are talking about neutron star or a black hole, that becomes a system. Okay, so even if when you are talking about the entire universe becomes the system here. Okay, so in the system, the systems are free to exchange heat. Okay, it can exchange heat, work and other forms of energy with the surroundings. Okay, now what is the surrounding? You can see here. So see here, there is a cup of tea. You can see in the picture, there is a cup of tea. Now when we want to talk about this cup of tea, what is the heat, what is the temperature of that cup, or what work it does, what energy it has. Okay, we are talking all about the cup. So here the cup becomes the system. Okay, and the surroundings. Okay, now let us suppose this is a boundary, or let us suppose the cup inside we are talking about this is a system. So here this is a boundary. Okay, we can consider the cup also, the cup's boundary also as a boundary. Okay, or this also as a boundary. Okay, it's the boundary. And what is this, the total thing? This is the surrounding. Okay, surroundings. Other than system, whatever it is there, that is surrounding. Understood? So here surrounding means not surrounding should not be very far. Surrounding should be in such a way that the system's effects should be influenced. Okay, see, if we are sitting in a cool place, if we are sitting in a cool room, okay, if we are sitting in a cool room, that becomes a system. When we are talking about that cool room, that becomes a system, and the walls of that room becomes the boundary. Okay, that is a boundary. And little space, okay, little space after this or outside of this room, little space, not much, that will also get affected in the coolness. No, that will also become cool. So we can say that this as surroundings. surroundings. We cannot say the far region as a surrounding because it is not affected by the system. Okay, I hope you understood. The surrounding means only some region where the system's effects are influenced. Okay. Now, this is a boundary, there is a surrounding, refers to everything outside of the system. Next, basic concepts of thermodynamics. So, we'll see what are the basic concepts. Thermodynamic system, a collection of an extremely large number of atoms or molecules confined with certain boundaries such that it has certain values of pressure, volume and temperature. So this is called a thermodynamic system. Okay, a collection of, let us suppose we take a gas, okay, we say which has a pressure, which has some volume, which has some temperature. So all this is known as a thermodynamic system with all these characteristics or properties, physical properties. Okay, thermodynamic system. Next, thermodynamic system can be controlled by mass or can be controlled by volume. Okay, now you see there are three types of systems: closed system, isolated system, open system. Okay, open system, closed system and isolated system. Let us see open system first. See, this is a system. Let us suppose this is a system. Okay, inside you are having some energy and you are having some mass also. Okay, energy and mass. So if the energy and mass can be exchanged outside, outside the energy can enter inside, inside energy can go outside, inside mass can come outside, outside mass can enter inside. So that means there is an exchange. Okay, there is an exchange of matter and energy. There is an exchange of matter and energy. In which system? In open system. Okay, if there is an exchange of matter and energy in the system, that system is known as open system. Okay, energy is also exchanged between the surroundings and the system. Matter is also being exchanged between the system and surroundings. So that is called as open system. Now coming to closed system, here we can see in the closed system only energy is exchanged between the system and the surroundings. System can give out the energy, can bring the energy from outside. But matter is not exchanged. You can see the intermark here. Matter is not exchanged. Only energy can be exchanged. Energy is exchanged. Matter is not exchanged. So that is called as closed system. Now coming to isolated system. In isolated system, neither of these two is exchanging. Neither energy is being exchanged nor matter is being exchanged. Nothing will get exchanged. Okay, I hope you understood about the open system, closed system and isolated system. Open system, energy and matter both can be exchanged inside to outside. In closed system, only energy is exchanged. In isolated system, neither energy nor matter can be exchanged. Okay, these are the three systems. Next, heat. We have been learning heat from the earlier classes, right? Heat, what is heat? Heat is a form of energy that is transmitted between objects or systems as a result of temperature differences. Because of the temperature difference only, heat is transferred. So heat is conserved energy, which means it cannot be created nor be destroyed. However, it can move from one location to another. Additionally, heat can be transformed into and out of various types of energy. That just now we have seen the thermal energy is can be converted to electrical energy, okay, mechanical energy and so on. So that is what it is saying here. Heat can be transformed into other forms. Next, work. What is work? This also we have learned in the earlier classes. We know the work formula, right? Work is equal to work W is equal to force into displacement. Yes, right? If there is something that has moved for a certain distance, okay, by applying some force, when we are applying some force and the object moves, then we can say that work is done. Work is said to be done, right? So work done by the system work done by the system or on a system, work done by a system or on a system during a process depends not only on the system's starting and final state but also on the path chosen for the process. Okay, it depends on the initial state and final state also, and it depends on the path chosen also. Okay, when a force acting on a system moves the body in its own direction, then work has been done. Okay, when a force on a system moves a body to certain distance in its direction, then we can say that work has been done. W is equal to F into S. So force and displacement combine to create the work. Force and displacement combine to create the work that is done or by a system. Fine. That is about work. Now what is internal energy? So these are all the terms which we will use in our thermodynamics. That is why we are learning here. Internal energy. The kinetic and potential energies of the molecules are added up to form internal energy. So when we take a cylinder in which there is some gas, okay, so it will have some kinetic energy that is being done, is there, and potential energy is also there inside the gas. So the molecules are moving, so rotational energy is also there. Okay, molecular attraction is also there, everything will be here. So that all sums up and become internal energy. Okay, basically we say the kinetic and potential energies of the molecules add up and give us internal energy. You can write Ke, kinetic energy, plus potential energy gives internal energy. Internal energy is denoted by U. Okay. Now you know kinetic energy. Okay, kinetic energy is due to its motion, the molecule's motion. So total kinetic energy and potential energy makes up a system which is known as internal energy. Next, some thermodynamic variables. What are some thermodynamic variables? We'll see. Now, pressure. Okay, pressure. Pressure is the force exerted per unit area. We know, right? Pressure is equal to F by A. Force exerted on a unit area, by a unit area, or per unit area, sorry, by the molecules of the system on its boundaries. Temperature. What is temperature? Temperature is nothing but the measure of hotness or coolness, how hot the body is, system is, or how cold the system is. So that is measured by using temperature. Volume. What is volume? Volume is a space occupied by any system. Okay, space occupied by the system. If this is the volume, say this is the volume, how much space system can occupy, that is known as volume. Internal energy, just now I have said you. Internal energy is the total microscopic energies of the system due to motion and interaction of its molecule. Next comes entropy. This is a new word for you. Okay, entropy. Entropy is a measure of degree of disorder. Okay, how disorderly or how randomly the molecules are arranged in a system, that is measured by using entropy. Okay, entropy is a measure of degree of disorder. We'll learn more about entropy in this unit. Okay, further. So, and indicates the unavailability of energy for useful work. So, whenever entropy increases, energy unavailability also increases. Means energy will lose. Whenever the energy is losing, entropy increases. Okay, we'll learn in detail about the entropy. Enthalpy, next one. Enthalpy is the sum of internal energy. See, sum of internal energy and the product of pressure and volume. The product of pressure and volume with the sum of internal energy, that is known as enthalpy, and it is denoted by H. H is equal to U plus PV. Next, Gibbs free energy. Gibbs free energy represents the maximum useful work obtainable from the system at constant temperature and pressure. Okay, how much maximum useful work can be obtained from a system? That is known as Gibbs free energy. We will also learn about this for the next. Helmholtz free energy. Helmholtz free energy is the energy available to do work when the temperature is constant. Okay, how much energy is available for us to do the work, for a system to do the work, when only when the temperature is constant. and volume also, constant temperature and volume. Next, number of moles, this you know, mass or number of moles represent the amount of substance present in the system. So that is the number of moles. Okay, I hope you understood all these variables. These are all, you are aware of all this, like pressure, temperature, volume, internal energy. Okay. Next comes intensive and extensive thermodynamic properties. Intensive. Intensive means the properties which depend upon the mass. Okay, the properties which depend on the mass are called as intensive properties. Like temperature depends upon the mass, pressure depends upon the mass, specific heat capacity also depends upon the mass. So these temperature, pressure and specific heat, these physical properties are known as intensive properties. Now extensive properties means it doesn't depend on the mass. An extensive property of a system depends on the system size or the amount of matter. Here a mistake. It does here intensive property does not depend on the mass. Okay, does not depend on the mass. So temperature, pressure and specific heat capacity doesn't depend on the mass, so they are intensive property. Now extensive property means they depend on the mass. Example, volume, energy, entropy, heat capacity and enthalpy. These are the properties that depend on the mass, so they are called as extensive properties. Okay, I hope you understood. The properties, the properties property which do not depend, okay, which do not depend on mass, which do not depend on mass are intensive properties. Intensive, which depends on mass, they are called as extensive property, right? Next, so you can see the examples, so you can see some of the intensive properties, intensive physical properties and extensive physical properties. So as I have discussed, intensive means does not depend on the mass, independent of mass, like pressure, temperature, density, concentration, melting point, boiling point, surface tension, viscosity and many more. Extensive means they depend on the mass, volume, internal energy, heat capacity, enthalpy, entropy, Helmholtz energy, Gibbs energy and etc. Fine. These are all the thermodynamic properties. Next. Next is thermodynamic equilibrium. Right. So thermodynamic equilibrium is a state of a system in which there is no net change occur within the system over time. That is the state of a thermodynamic system in which macroscopic properties such as temperature, pressure and chemical composition remain constant. See, let us take two systems, okay? If in these two systems the temperature, if the temperature is same or if the pressure is same or if the chemical composition is same, then we can say that these two are in thermodynamically in equilibrium with each other. These two systems are in we can say that these two systems are thermodynamically equilibrium, right? So if we say that the temperature in let us suppose this is as a system A and this as a system B. If the temperature in A is T1 and if the temperature in B is T2 and T1 and T2 are equal, okay, they are in thermal equilibrium. We say the systems are in thermal equilibrium. The temperature of the system remains constant. Okay. So if the pressures are equal or if the pressure difference is not there, if there is no pressure difference between system A and system 2, then we say the system are in the two systems are in mechanical equilibrium with each other. Okay, and if we say the concentration of reactants or the number of molecules are same, they do not change, then it is chemically equilibrium. Okay, so this is about the thermodynamic equilibrium. Next, thermodynamic processes. Thermodynamic processes. A process in which the thermodynamic variables of the thermodynamic system changes is known as thermodynamics process. How many thermodynamic process can be seen here? Isobaric, isothermal, adiabatic, isochoric. Okay, so I'll explain you what is isothermal, isobaric, adiabatic, and isochoric. Isothermal process is a process that occurs when temperature remains constant. Okay, when the temperature remains constant and the work is being done or the process is being done, then that process is known as isothermal process. Isobaric process is said to be done when pressure is constant. When pressure is constant. Okay, adiabatic process is said to be done when there is no net flow of heat. No net flow of heat. No net flow of heat. Means dq is equal to 0. Heat is constant. Okay, heat is constant. Q. Heat is constant. Okay, isobaric, pressure is constant. Isothermal, temperature is constant. Adiabatic, heat is constant. Okay, next isochoric. In isochoric, the process volume will be constant. No change in the volume. Okay, these are the four processes. Understood? Isobaric process in which the pressure is constant. Isothermal, you can remember, isothermal, temperature is constant. Adiabatic, no heat exchange is there, heat is constant. Isochoric, volume is constant. Right? So this is the PV diagram, we say PV diagram, where the pressure and volume is taken in on the y-axis and x-axis respectively. So you can see the graph. For isobaric, you have a straight line like this. For isothermal, this for isothermal, this for adiabatic, okay, and this for isochoric. Okay, we'll see in detail about isothermal and adiabatic processes in our unit. Okay, this is what I explained here. Isothermal means constant temperature. The process takes place at constant temperature, but pressure and volume can change. Okay, dt is equal, change in temperature is not there. T is constant. T is equal to constant. Temperature is equal to constant. Then change in temperature dt becomes 0. Okay, in adiabatic, Q is equal to 0. Okay, there is no exchange of heat between its surroundings and system. Okay, Q is equal to 0. No net heat is flowing. For the exchange of heat between the system and surrounding, there is no time or there no process. Okay, no heat exchange is happening. Next, isochoric. In isochoric, we can say volume is constant. Okay, volume is constant, so dV is equal to 0 as volume is constant. You can see here constant volume. Isobaric means constant pressure. Constant pressure dP is equal to change in the pressure is 0. You have to remember, when the pressure is constant, then change in pressure becomes 0. Next, cyclic process. A cyclic process consists of a series of changes that returns to system to its initial state. Cyclic process is nothing but it is also called as reversible process. We can say it as reversible process. Okay, where the system can come to its original position again, to its initial position. Okay, these are about the processes. Next, so you can also see the table over here. Adiabatic means Q is equal to 0. Isothermal means dt is equal to 0 because temperature is constant. Isobaric, pressure is constant, so dP is equal to 0. Isochoric, volume is constant, so change in volume dV is equal to 0. dt means change in temperature. dP means change in pressure. dP means change in the volume. So whenever these terms are constant, then its change will be 0. Change in the system is 0. Okay, cyclic process, energy is 0, enthalpy is 0, change in energy is 0, change in enthalpy is 0, change in pressure 0, change in volume 0, change in temperature 0. That is cyclic because it is coming to its initial position again, no? So everything will, the change of every property will be 0. Next, moving ahead, we have laws of thermodynamics. Okay, so laws of thermodynamics, I think we'll start in the next video. Okay, so till here it's okay, we'll stop here. So I hope you understood. Listen again so that you can understand properly. Thank you.